Someone looks to be surprised by by my voice. So we're happy to have now Jeroen Schillewaert. Is it correct? Is it correctly pronounced?
It's close. It's close enough.
No. Who comes from Auckland and who is going to introduce us to highly regular expander graphs. So up to you now. Thanks.
Thank you very much, Thomas. So yeah, I'll speak on highly regular expander graphs, and I've put the highly regular in parentheses because I will mainly focus on expander graphs. I got recently interested in this topic and managed to construct some highly regular ones using geometric methods. So my main area is geometry rather than expander graphs, but nevertheless, I'll tell you a little bit about them. I will assume that you have not heard of them before. So if you have, you might recognize a lot of stuff. So here's a brief overview of my talk. So as I said, I will start with definitions and basic notions on expander graphs. And then this will become an tutorial in nature. And then I will show how you can also investigate expander graphs using algebraic methods, eigenvalue methods. So that's why the word spectral expansion is there. These are very useful tools to investigate this thing. Then in my third topic, I will discuss Ramanujan graphs. These are graphs which are optimal from the point of view of expansion. And I will discuss two classes, one of which was already discussed to quite some extent in Bo's talk. And then finally, I will spend a couple slides on the results we actually obtained recently on highly regular expander graphs. So first, a bit of motivation. So expander graphs go back to the 1960s, where they were introduced by engineers to model communication systems. And when you have a communication system or a network, you can of course model it by a graph, by having your devices to be vertices and the connection between your devices to be edges. So there was a lot of interest in communication systems back then, still is today. And you can assume that information propagates along edges in 1 unit of time. So you have, say, some information that's sitting at some vertex or node, as the engineers would call it. And then that information is starting to flow through the network 1 bit at a time. And of course, what you would like is that every set of vertices should be well connected to the remaining vertices to ensure quick transmission of information. Especially back in those days, the devices were quite slow. You wouldn't want that you would see the 1-0 in the World Cup when it's already 2-0, right? So you have to make sure you're quick. But on the other hand, you don't want your system to be incredibly expensive. I mean, if your number of edges is huge, absolutely huge, your costs will be tremendous because you have to pay for, well, back in the day for copper. These days you have to pay for optical fiber. So you need to make sure you don't have too many edges. So we have two antagonizing conditions here. So on the one hand, it should be quick. And for that, you're helped by having a lot of edges. On the other hand, that's bad news for you. So how can we sort of align these two requirements? That's the task at hand. So we're gonna look at K regular graphs. So K will be a fixed number, and K regular means that every vertex is connected to exactly K neighbors. Why are we gonna do that? Well, if you just ask if the only thing you're interested in is quick transmission, then the best graph in the world on n vertices is the complete graph, Kn, because you can go from any vertex to any other vertex in 1 step. So that's, from that point of view, there is nothing better than Kn. But as we said, you don't want too many edges. If you have many edges, you have to pay a lot of money. The number of edges for the complete graph on n vertices is quadratic in the number of vertices. So n times n minus 1 over 2. So you can see that if n starts to grow, this is quickly gonna become a big number and it's gonna become too expensive. So therefore, we're not gonna consider this graph. And we're gonna restrict to K regular graph, where K will be fixed. So we will choose K once and for all. And then we will look at how many edges such a graph has. And that's easy to check by double counting. Namely, you look at pairs, edges, vertices. Every edge has 2 vertices on it. Every vertex is contained in k edges. So you get 2 times E is k times V, or when I rewrite it, E is equal to k times V divided by 2. This time, this is linear in the number of vertices. So before we had quadratic growth, this time we only have linear growth. So these are much, much better from the point of view of the cost that you're gonna have. But of course, are they still gonna be good for transmission of information? That's the big question. And I put family there in bold. This is for the following reason. You often hear people speak about an expander graph, which technically doesn't mean much. It only means much when you look at a family of graphs, an infinite family of graphs where the number of vertices goes to infinity. I will explain to you in a minute why it is important not to speak about one graph. Okay. So here is the definition. Looks maybe a little bit daunting if you have never seen it before. So I will try to unpack it. So a finite graph X is said to be epsilon expanding. So epsilon is a parameter. And if it's isoperimetric constant, sometimes it's called the Cheeger constant. What is it? It's that property there, h of x, the minimum, blah, blah, blah. So basically what we're going to look at is we're going to look at a subset of the vertices of X. And we said that our requirement was that such a subset had to be well connected to the other vertices. So by partial A there, I denote the edge boundary. This means these are edges which connect vertices that are inside A with vertices that are outside of A. So if you're well connected, this will be a reasonably large quantity. And of course, to make sense of this, if your graph grows, you need to look at some sort of ratio. So we look at the ratio between how many are going from A to outside of A, divided by, and then we take the minimum of A and X over A. And that gives you the isoperimetric constant. And you see, I take the minimum there of A and the complement of A, so that means that I could as well restrict to sets of size at most X over 2, just by looking at that minimum, because the boundary value is going to be the same regardless of whether I look from inside or outside. And here you can already see that speaking about one graph being an expander doesn't make much sense, because I can make any graph an expander. I just need to take epsilon small enough, right? If I take epsilon, I think smaller than 2 over X or something, then it will always work. So that doesn't make sense. The whole point is that you can look at a family where the family becomes larger and larger and larger, and epsilon remains the same. That is the art. Okay, so that's why we need to talk about a family of expanders. So now we have a family Xn parameterized by n, a family of k regular, so k is fixed, finite connected graphs. I mean, of course, they have to be connected, so otherwise somebody's not going to get any information at all. And we let the number of vertices go to infinity, and we want that there exists an epsilon independent of n, such that the isoperimetric constant is at least epsilon for all n greater than or equal to 1. Okay, so very important family of expanders. Okay, we've defined this concept, which is a little bit tricky. So the first thing to answer is, well, do expanders exist? I think you will suspect the answer is yes, otherwise we could all go home now. And we first look at k equal to 2, so 2 regular graphs, but they are going to be bad, because think about it, if you have a finite 2 regular graph, what does it mean? You have a finite graph and every vertex has 2 neighbors. Well, the only such graphs are cycles, and it's an easy exercise. But cycles are very bad from the point of view of expansion, because even if you take half of the cycle, so you take half of the vertices, there are still only 2 edges, namely from the boundary vertices to the continuation of the cycle. So the boundary of A is 2, and then if A grows linearly with n, it means that if I look at a cycle of size n, this isoperimetric constant is of the order 1 over n. But as n becomes bigger and bigger and bigger, this goes to 0. So it will be impossible for me to find an epsilon independent of n, which works for all n. No matter which epsilon I take, if I take epsilon I take, sorry, I can make n large enough so that I will go below it. Okay, so that's bad news. However, there's also good news. The good news is if I avoid this sort of anomaly of k equal to 2, then they exist, and they actually exist in abundance. So this is a theorem going back to Pinsker in 1969, although it turned out that Barshdin and Kolmogorov had already looked at this same problem in 1967. So we let k a fixed integer, at least 3. I have to take at least 3 because of what I just said for cycles. Then, given any epsilon greater than 0, the proportion of k regular graphs which have isoperimetric constant less than epsilon goes to 0 for n going to infinity. So this is immediately gives you the existence of families of expander graphs. So this is a good result. So now we know that our objects exist, so we can talk about them. And this has applications in computer science, so in the theory of error correcting codes, communication networks and algorithms, and medicine. So this first thing, these applications in computer science, that was the point of view of Pinsker's paper. And Barshdin Kolmogorov looked at networks of nerve cells of the human brain. So yeah, they are important also from the point of view of applications. Of course, this is all good and well. We have shown existence, but if you want to eat something, it's better that you get a dish in front of you than that somebody tells you that there's food somewhere. So what about explicit constructions? So the first explicit examples were provided by Gregory Margulis, one of the greatest mathematicians of the 20th century, using the so-called Kashdan property T, which is a fancy and important property that connects many areas of mathematics. So this seems to be a theme, although expander graphs have a, okay, it was a little bit tricky, but in the end, it's a fairly mundane definition. It turns out that if you want to construct them explicitly, the mathematics involved immediately becomes very deep, and it seems to be fairly unavoidable. Okay, so I will discuss these Margulis examples a little bit later in the talk. I have not, well, I had written a proof, but I think it's a little bit too much on a Friday evening. So first of all, a nice property about expander graphs is logarithmic growth of diameter. So we said that our goal is for these graphs to be well connected, sort of, and rapid transmission of information. Well, if we said that information was flowing with 1 unit of time, it would be good if between any 2 nodes or vertices that we don't have to travel for too long. So when our graphs become really huge, it's interesting if the diameter only grows logarithmically, because it's a very slow growing function. That would be very good for us. So here is such a result, or lemma. Let x be d-regular. Well, I should probably have stuck with k, but anyway. With isoperimetric constant h of x. So we are assuming that we have an expander with that h of x, or not expander, this is for an individual graph, but the point for expander family will be that we can keep the same h of x. And I set this c equal to 1 plus h of x over d. The reason for that will become clear in a minute. Then the diameter, you can see, grows logarithmically, because c is basically a constant, so it grows logarithmically in x. How do you prove that? Hands-on. Suppose that I look at a vertex v, and I look at the ball of radius r-1 around v. That means all vertices which are at distance at most r-1 from v. And suppose that this ball has at most half of the elements of x. Okay. Because I'm assuming that I have an isoperimetric constant h of x, it means that the boundary is at least h of x times the number of elements in there. Because remember, the ratio was at least h of x, so I just moved this to the other side. Okay, so what I'm going to do here is I'm going to show that BR minus 1 of V has a lot of elements in it. That's my goal. So I have deregularity. So therefore, if I look at the sphere of radius r at V, I mean, if I'm going to leave the ball of radius r minus 1, I'm going to leave it by ending up in the sphere of radius r. But if you look backwards from that sphere, every element in that sphere has at most d neighbors, and in the best case, they're all inside that ball. So d times SR of V is at least equal to the boundary value. So if I then put it in the denominator, I get that bound. And using the previous line, I can simplify like that. So what have I done now? I have shown that the art layer in the sphere has a lot of elements. And now, of course, if I want to count the ball up to a certain radius, that's just the union of these spheres. So that's what I'm going to do. So BRV is hence greater than or equal to C times BR minus 1V. And repeating this argument, you see that this grows exponentially. Okay, as long as this ball has size at most x over 2. Okay, so I mean, if you can't follow all the details, I mean, I know it's a bit quick, but this a fun exercise to do, and I leave the finishing the proof to you as an exercise using some overlapping spheres. But so in summary, what has happened here is I have shown that these balls have lots of elements, and therefore the diameter cannot become too big. Okay, now I'm switching gears to the eigenvalue methods. So I told you we can investigate this from the point of view of algebraic graph theory. And I'm going to define the Laplace operator on graphs. So these names are chosen from Riemannian geometry because they sort of emulate similar concepts, but it's just hands-on combinatorics. So don't be deterred by the terminology. So I take a finite connected k-regular graph. Then the Laplacian is an operator giving from L to V to L to V. So what is L to V? These are the functions from V to C, such that if I sum the values over all the vertices, it stays finite. Here, this is automatic because I've said that V is finite, but this concept makes sense even for infinite graphs, and then you could have some restrictions, okay? And basically what it does is it takes a function f, and it sends it to a function delta of f, and so I need to declare what delta of f is on a given vertex x, and it's k times f of x minus the sum over all the neighbors of x of f of y. So that's how this new function behaves. Okay, and so the claim is that this operator is going to give us information about the expansion of the graph, so about what we defined before. So I equip this with the Hermitian scalar product. Just you look over all the vertices and you sum. I've written it there with a bar because a priori the values could end up in C. Okay. And I say is a non-negative operator. I mean, what do I mean by that? Well, an operator always has eigenvalues. If you don't like operators, because we're in the finite case, you can think of matrices, because everything can be expressed with an adjacency matrix, and the adjacency matrix is for the second part of the sum, this sum over the neighbors, and the first part is then just k times identity. And so the non-negative operator, this is because the eigenvalues, I can list the eigenvalues as lambda 0 equal to 0 is the smallest one, less than equal to lambda 1, etc. So then the other eigenvalues. And lambda 0 has multiplicity 0 because x is connected. So if you have seen this before, you might have seen before that the trivial eigenvalue is usually k instead of 0. But that's because usually you look at the eigenvalues of just looking at the adjacency matrix. But here I have done k times identity minus that. So therefore, k minus k, the trivial eigenvalue becomes this 0. What is important now what is going to be important is how big this lambda 1 is. So lambda 0 has multiplicity 0, so there is some gap between lambda 0 and lambda 1. And what we're going to see in a minute is that the bigger this gap is, the better our expander is. So, and this is why it's a useful tool, because once you have this, you can use matrices, you can compute eigenvalues. I mean, that's sort of easier to do than going over all these subsets. All right, so let's have a look at this lambda 1, the so-called spectral gap. But before that, the non-negativity of the Laplace operator. So I need to keep an eye on my time. I think I'm good. So what you can always do on a graph is you can orient the edges. Just for every edge, you say like, well, one of them is the start and the other one is the finish. And you call the start E minus and you call the finish E plus. So you choose that. And then you can define a so-called co-boundary operator. Again, this is a mundane operation. So we had a function on L2V, and we're going to associate to that a function on L2E. So what does that mean? We're going to say for every edge what the function value on that edge is. So we have a function f on the vertices, and we associate to that a function df on the edges. So I need to use my function f on the vertices, and the way I do this is by saying that df of the edge E is f of the finishing point minus f of the starting point. Okay. The details are all not so important for now, but so I have associated to f a function df. And then you can also define a so-called adjoint operator, d star. So this is one that goes in the other direction. So if you have a function which operates on the edges, you will associate to it a function which operates on the vertices. And the term adjoint means that I want the property that I listed there, that the inner product of df with g will be the same as f inner product with d star g. Okay. It turns out you have to take this form, so you can actually write it down explicitly what it has to be. All right, so it's the sum, if you want, so we have a psi, which is a function on the edges, and now I associate to that d star of psi, which is a function on the vertices. And what I do is, if I want to know the value at x is in a bunch of edges, and x, since I have chosen an orientation, x is the finishing point in a number of them, and x is the starting point in a number of them, and I just make that sum. And lo and behold, it would not be called a Laplacian if it was not equal to d star d. So exercise, I mean, it's just writing out a few lines. It's a little bit tricky, but it's not intrinsically difficult. Then d star d is equal to delta. And what is beautiful is that I told you at the beginning of the slide that we're going to orient the edges. And so this d and also this adjoint operator will depend on this choice of orientation. But the combination d star d does not. That's quite interesting. And from this, we can, of course, obtain the non-negativity of the Laplace operator. There is a variational principle, which you may have heard or not, that you can obtain lambda 1 the way I write it there. So you look at all the functions which are orthogonal to 1. So remember, the inner product was the sum over all the vertices of fx bar gx. So this just means that the sum of the values adds up to 0. That's what it means to be orthogonal to 1. So why is it positive? I need to know that the denominator is clearly positive. So I need to know that the numerator is positive. But this, of course, follows from what we have just done in this slide. Namely, this will be equal to the norm of df square over f square. I realize this is all very fast. If you think this is quite nice, I can recommend the book of Davidov, Sarnak, and Alain Valette, which is a very, very good book. So now I'm going to do half of the Cheeger-Boozer inequality. So neither Cheeger nor Boozer worked on this inequality, but they have a similar result in the Riemannian geometry, which is called Cheeger-Boozer inequality. But this was actually done by Noga Alon. And we're going to do the easy direction, which is that the lambda 1 is less than or equal to 2 times h of x. So h of x was our isoperimetric constant. And so this measures how well the set is connected. The bigger h of x is, the better connected it is. So here you can see that if we're going to find a big lambda 1, we're going to have a big h of x, we're going to have good expansion. So the other half of the inequality is saying that you can also bound h of x from above by a function of lambda 1, which then shows that essentially they are measuring the same thing. So if one is good, then the other one is good. This is the easier direction. If you tuned out on the previous slide, then, well, you can tune back in if you wish to do so. So how we're going to prove that? Well, if I assume that my isoperimetric constant is equal to h of x, this h of x was a minimum taken over a bunch of subsets. So that will mean that there should be some subset A which attains this isoperimetric constant, right? And by my remark in the beginning, I can also assume that this A has at most n over 2 vertices. If not, then take its complement. Okay. So I have a set A, which has at most half of the vertices of V, such that h of x is equal to the boundary of A divided by A. And so now I need to somehow bring lambda 1 into this game. So what am I going to do? Well, we saw on the previous slide that you can compute lambda 1 with this variational principle. So what I'm going to do now is I'm going to define a function which is quite good with respect to lambda 1. So I define xi a of x. So xi a is my function, and I define it to be this very straightforward function. If x is in the set, then it will be the size of v minus a. If x is not in the set, then it will be that should be minus the size of a. Okay. So first of all, if you look back here, sorry, remember that we were looking at these functions f over which were orthogonal to 1. So if I want to use this function to compute or to say something about lambda 1, I should check that it's orthogonal to 1. And well, if it's not, then I'm in trouble. So it should be orthogonal to 1. Of course it is, because what is it? Well, you have a vertices for which you get v minus a, and you have v minus a vertices for v minus a, so it cancels each other out. So you're allowed to use it as a so-called test function for lambda 1. So what that means is we can compute the value of this expression that we had there, and lambda 1 will be no more than this, because lambda 1 was the infimum over everything. So if I can compute the value here, and if that value is at most 2 times h of x, then I will be done. So now we need to compute. So one of the things we had to compute was the norm of xi a square. I mean, all the information is given there. It's a times, for the vertices that are in A, I need to square v over A. For the vertices that are in V, in the complement of A, I need to square minus A, which gives me A square. And so if you add it up, you get the expression on the right-hand side there. Now, we need to compute the boundary. Well, look at d xi a, so that was this other function. Remember what d xi a was? It was you subtract, it's the difference of the finishing value and the starting value. Now, if you stay in the same part, then these values are the same. So if you don't go from a to the complement, then you will get the same value. So then the difference will be 0. If you do go from one to the other, then depending on whether your starting point was in the complement or not, you get plus or minus n. Why n? Because it's v set minus a and then this a. So the sum of those two is v, which is n. So it can be plus or minus n, but that won't bother us because we're going to square it. So now lambda 1 is at most this value. And I have used here for the last inequality, I have used that the complement of A is at least n over 2. So you see that this gives us half of this Cheeger-Boozer inequality. So I find it quite interesting that you can use these eigenvalues to actually say something about this purely combinatorial property. So as I said, the other half of the inequality is much more involved, but you can read it in that book. Okay, any questions so far? Okay. So now I want to come to the explicit construction of these expander graphs. And as I said, it's a little bit involved to construct these. And many constructions use a bit of group theory. And more particularly, well, using groups, that's all good and well. So we will need to be able to associate graphs to a group. And so the standard mechanism to do that is by means of Cayley graphs. So let's say G is a finitely generated group and S is a finite symmetric generating set not containing one. Okay, so the generating set, so every element of G can be written as a word in these letters in S. So the Cayley graph is a graph for which the vertices are the group elements, and you are going to connect two vertices if they are of the form G and SG, where G is in G and S is a generator. So now you can see why I chose S to be symmetric, because I want to get an undirected graph. So I want that if there's an edge from alpha to beta, there is also an edge from beta to alpha. And if I ensure that S is equal to S inverse, then I can always do that. And not containing one, that means that I have kicked out all the loops. If you have one, then you would have a loop from a vertex to itself. So this is some conditions to make it a nice graph. So that's the Cayley graph associated to a group and a generating set S. So it's not true that like a group has a particular Cayley graph. It depends on G, but also on S. And it turns out that if you put, well, it turns out it's immediate. If K is equal to S, so if you have K elements in your set S, then of course you will have K neighbors because the edges are of the form G, SG. So by varying S over the set big S, you get K neighbors. It's connected and vertex transitive. You can see that because G acts transitively on the vertex set by right multiplication. If I multiply with H on the right, then my new edges become GH and then SGH. Yes. Okay. And then, well, this, yeah, I will not dwell too much on this, but my Laplace operator from before, I can now like apply it in this context. And for those who know what this is, I'm looking at my time. You can write this now in the form S times the identity minus something called the left regular representation. I will not dwell on this. You can look up more on that if you want to. So, but the important part is, given a group, you can associate a graph to it, and we're going to try to use this to construct expander graphs. So the question is, which groups? I mean, it's all good and well to have this abstract construction. We have to put some groups in it. So here is an exercise for you. Well, maybe you want to use abelian groups. So the question is, if you put in abelian groups, would it be possible to get a family of expanders? So that's an exercise for you. Given that I'm going to use non-abelian groups in a minute, this will give you an inkling as to what the answer is. And for that, I need more complicated groups. So a group is called residually finite if there exists a decreasing sequence of finite index normal subgroups such that the intersection is the identity. So let's just say this is a nice group theoretical property. And then there's a more fancy theoretical property called Kazan property T. And you can trust me on fate that SLDZ for D at least 3 has both these properties. So especially proving the second property is quite difficult. So, but what it means is SLDZ has very nice properties which will help us to construct an expander. And this is what Margulis did. So I'm not gonna discuss the proof. So G is a group that is equipped with nice properties. So as I said, you can think of SLDZ with D at least 3. Then you can construct a family of expanders. Okay, so this is the first explicit construction of such expander graphs. And you can see that we are already using a number of fairly involved concepts from mathematics, different areas of mathematics. Questions so far? Okay. So I'm happy that I left out the proof of the Margulis theorem because I'm already short on time as we speak. So now something about the asymptotic behavior of eigenvalues and expanders. So I told you that lambda 1 was related to h of x, so that if lambda 1 was big, then we had good expansion. So now we can ask, in some sense, what is the best expansion we can get? And that is given by a theorem of Noga, Alon, and Bopana. So this time, mu of I denotes the eigenvalues of the adjacency matrix. So that's, I mentioned this before, in my operator delta, I had k times the identity minus the sum over all these neighbors. And therefore, my trivial eigenvalue was the 0 eigenvalue. Here, I don't have k minus, I just have these last ones. So the trivial eigenvalue is k. And so the spectral gap then is, if the trivial eigenvalue is k, then the second largest one is smaller than k. And the bigger this gap is between k and this second largest one, the better the expansion. And this theorem tells you that there is a limit to this. You can't expect that this second one is going to go all the way down to 0. It's going to be at least 2 times root k minus 1. Okay, so you have your k, and then you have the second largest one. You want to maximize this gap. This Alon-Bopana puts a limitation to this. And these Ramanujan graphs are going to be the ones that are optimal with this respect. So Alon-Bopana says, this is the best you can hope for. And a Ramanujan graph shows that your hope can be fulfilled. So your best hope can be given. So as I said, they have optimal spectral gap. And since the spectral gap and the expansion coefficient were related, they are optimal with respect to expansion. So before, we already saw that this Margulis construction was already highly non-trivial with this Kazan T and all the rest, all these bells and whistles. Here it's yet another level of difficulty. It uses very deep number theory and algebraic geometry, which uses the very deep results by Pierre Deligne. And there are 2 constructions that I will briefly discuss of these Ramanujan graphs. So the first construction is by Lubotsky, Phillips, and Sarnak, and that's the construction which is described in a lot of detail in the book by Davidov, Sarnak, and Valette, except that in the end, these results by Deligne have to be used as a black box because, well, that's too difficult. And then the second construction I will briefly mention is Peiser's construction, which Bo has already done in his excellent talk. And so actually, I'm going to give 2 fairly hands-on concrete constructions of these Ramanujan graphs, but you can actually study them in one overarching framework, which is the Bruhat-Titz tree. So I won't dwell on that too much, but with the Margulis construction, I didn't say that, but basically these graphs, they all come from some overarching infinite objects, and then you take quotients, and like that you get a family that grows. And here it's the same. I will give hands-on constructions, and you will see it depends on a parameter, and that can then grow. But you can also describe it as quotients coming from an infinite object, which is this Brouhat-Hitz tree. And that's actually the better way to look at this, but it's quite technical. So here goes the hands-on Lubotsky-Philip Sarnak construction. Take two distinct odd primes, both 1 modulo 4. Why? We'll see in a minute. It's a classical result by Jacobi that if you have a prime which is the sum of 4 squares, you can do that in p+1 ways. You might have seen it that it's in 8 times p+1 ways, but because of these extra restrictions that I put there, this is going to reduce it to p+1 ways. Okay, so look at that. Take epsilon squared to be -1 modulo p, and define a matrix A in PGL2Z as follows. A is x0 plus x1 epsilon, etc., etc. Okay. The details are, you can look at them at ease if you like. The determinant of A is L modulo P. Well, this is easy to see. Look at the determinant, you get x0 square, and then you get minus x1 square epsilon square, but epsilon square was -1 mod P, so that gives you x0 square plus x1 square. And then if you add the two others, you will get plus x2 square plus x3 square, but that was equal to P. Okay. Then you can look at the images of these matrices under this map, and you look at this Cayley graph, and this gives you Ramanujan. So, I mean, as I said, it's probably too difficult to remember all this at once, but the point is that this gives you a very explicit construction of a Cayley graph, and it turns out to be Ramanujan. Second construction, this is the Peiser graph. So these come from elliptic curves, and everything I say will be sort of a version of what Bo has already told you. So you can have the Weierstrass equation if the characteristic is not 2 or 3. And then you can define a so-called J invariant that tells you when elliptic curves are isomorphic, which only depends on A and B. So that measures this. And a super singular elliptic curve, as Bo told us, is one such that the endomorphism group is a maximal order in the unique rational quaternion algebra, which ramifies only at infinity and P. And so what we're going to do is we're going to set up a graph based on these super singular curves. So in a isogeny of degree L, we have a rational map which preserves the identity. And the degree is the number of elements in the kernel, which is the same as the degree of the rational map. I'm doing all of this quickly because Bo spent lots of time on the previous talk on this. Okay. So here's Peiser's supersingular isogeny graph. As vertices, you take these isomorphism classes of supersingular elliptic curves, which, as I said, are witnessed by these J invariants, and it turns out that they are defined already over fp squared, and there are roughly p over 12 vertices. So I use the squiggle there, which is nice. You can never be wrong if you put a squiggle because it can mean anything you want. But here I'm not lying much. And then, well, I have a graph, so I have to also say what adjacency is. So adjacency will be given by isogenies of degree L. And this turns out to be an L+1 regular graph because of the L torsion group is a direct sum of 2 cyclic groups. So in there you have L+1 cyclic subgroups of order L. So this is basically the number of points on a projective line. And Peiser proved that this graph is Ramanujan. And again, he used the same work by Deligne on the Ramanujan-Petersen conjecture. And so if at first this seems surprising that these seemingly extremely different constructions both need the exact same work of Deligne, this comes, as I said, because you should actually view them in this same framework of the Brouhat-Hitz tree, where you will see that the constructions are similar. And the reason this is interesting for cryptography, well, Bo talked about this at length, is that finding paths between two vertices should be at least as hard as computing isogenies between supersingular elliptic curves. And since the latter is believed to be a hard problem, also this should be a hard problem. Okay. So now I come to the actual reason that I got interested in this topic, which is the concept of A0 up to AN regular graphs. So let me define it first. I have 5 minutes left or something. Yeah. So let X be a graph and V a vertex. And now I want to define higher regularity. What does it mean? I will throw a bunch of definitions here at you. Don't read them. Listen to what I say. Regularity means that every vertex has the same number of neighbors. Now, A-B regularity, A, B regularity will mean that not only do you have the same number of neighbors on each vertex, but on top of that, you have the same number of triangles on each edge. ABC regularity means then that you have the same number of K4s on a triangle, etc., etc. So it are graphs which are regular, and also if you look at the neighborhoods of a vertex, they stay regular. And the number of times you can repeat this process is the level of the regularity. Okay. So last year there was a paper by Chapman, Lineal, and Pillet, where they study properties of AB regular expander graphs in the context of PCP testing. I don't know anything about that, so don't ask me. And they constructed new families of AB regular expander graphs. So it's not so difficult to construct AB regular graphs. It's harder to construct them so that they also form an expanding family. And they concluded their paper with the following open question. Do higher dimensional constructions exist? In particular, does there exist a family of ABC regular expander graphs? So this means every vertex has A neighbors, every edge is in B triangles, and every triangle is in C tetrahedra. Can you describe such graphs? Already, this is not so easy. You can try it as an exercise. But more importantly, can you construct a family which also expands? And the answer is yes. So earlier this year, before the corona struck very hard, we had Alex Lubotsky visiting us, so one of the world leading mathematicians, and together with Marston Condor, who's also here at Auckland, and François Tilmany from UC Louvain, we were able to answer this question in the positive. And this slide will not be very informative if you don't know anything about Coxeter systems. So let me maybe just say that we have a geometric method to construct higher regularity expander graphs. And then, of course, we have a couple of conditions here. So the question is, can we find interesting examples that have all or satisfy all our conditions? And so I will conclude with the direct applications of the main theorem. So we get an infinite family of 120, 12, 5, 2 regular expander graphs. So note, Lineal, Chapman, and Pillet asked for ABC, but we can do ABCD. And actually, we can do better. So these string Coxeter systems of my previous slides, they come from regular tessellations in high dimensional hyperbolic spaces, but that's not strictly necessary if we loosen our framework a little bit. So if we also consider tessellations which are not necessarily regular, then we can find other examples. And the best example we could find is I have to read out these numbers, I'm sorry. 2,160, 64, 21, 10, 5 regular expander graphs. So that's our champion, which is an A, B, C, D, E. So we can do C, D, and E. And very interestingly, this one is intimately related to E8, which you probably know is one of the most famous symmetry groups. But well, we have answered Chapman and Lindell and Pellet's questions in the positive, but this really seems to be the end of the line for our approach. So A, B, C, D, E, like we have tried fairly hard to get past 5. We were unable to do so. So I think it's a very interesting question if you can construct with whatever means possible to you, expander graphs with higher regularity. I should note that actually, if you're not interested in expansion, but just in the regularity, you can go to any N you like. And that has been, this is in a recent paper by Ehud Friedgut. But if you want expansion, none of his constructions are expanders. If you want expansion on top, more than 5, we don't know. All right, this was quite a lot of information. Hope you enjoyed it nevertheless. Thank you very much for your attention. Are there any questions? No, we don't want to do the proof of the Margulis theorem.